So let me be systematic and start from here. So remember last time, okay, let me just tell you what my aim is today. One is to construct for you the Fokker-Planck equation. Then tell you about entropy production. And then apply those ideas in some simple active system models. And I will then close with sort of a couple of active matter phase transitions, which connect somewhat tenuously to the rest of the talk, but I thought would be fun, and which have a substantial experimental component as well. So let's see how we go. So last time, I promised you that we'd work out the, notation is going to be a problem. What did I call my dynamical variable last time? Q? Okay, doesn't matter. So, sorry? X? Okay. Okay, let me just, no. I have equation numbers here, so let me try to use them. Doesn't make any sense, excuse me. Sorry, just give me a second. I seem to have lost a page. I think I can function without it, but if I can find it, I'll be much happier. No. Either I've lost a page or... It doesn't matter. So imagine you have a Lingerie equation. I need a specific form. Just give me a second. So let's say I have a Lingerie equation of the form and what I want to do is to build the equation for the probability of finding a value and what I said was the following. I sort of started to sketch this story. Let's divide time into slices. So let us say this is some time t1, this is some time t2, t3, etc. And now imagine you pick one realization, you draw one function f, then what will happen is you will get, I really shouldn't be even connecting the dots, you will get it, the particle here, 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 there, maybe there, and so forth, right? And let's call this trajectory x sub f. Is that big enough? So x sub f of t equals solution. Excuse me? So I did draw them. This is the solution to this equation. So you draw an f, you get one answer to this differential equation. To, I don't know, what to call this 1, 2, 1 for a given f. Now, if f wasn't distributed, if f was a unique function, then clearly the probability density at each slice is just a delta function at where the particle lands on that time. So because it's always there. So if you, therefore, in general, what will you say? In general, you'll repeat this experiment a zillion times and you'll get a sprinkling of dots here. And clearly, the probability, therefore, is just the average of this guy, where by this angle bracket, I mean average over realizations of f. Okay. Now what you can say is, we want to build this equation of motion. There are various ways of doing it. Let me do it by saying that the probability that the particle finds itself at x at a time t plus delta t, given that it is at some point x prime at t, is what? It's the probability of x changing by some amount delta x, right? So it's where delta x is by definition just x. Delta x is the probability that x minus x prime has a value delta x, right? Is x. Am I doing this right? Writing it slightly weirdly. My notation is sort of going to hell. I should really put subscripts f all over the place. But you know what I'm saying here. So let's just look at the object delta of x minus x prime minus delta x. Yes. Yeah, no, at the moment I'm saying just the probability of x, so I should really say the probability that x makes a change, the probability of a change delta x in a time delta t, right? Yeah. I can write this as delta of x minus. Let me now formally just write this. Right. And I'll stop here, and I'll tell you later why it's okay to stop here. What we want to calculate is the following. What we want to go back to is this picture and say that the probability of ending up, let us say this is time t, at a given point x, given, let us say that you started at t naught at some point x naught, is the probability that at any time t prime in between, you went from x naught to some point x prime, and you went from x prime to x, averaging overall, integrating over all possible x primes. So let me write that out. So for any intermediate slice t prime, irrespective of what went on before or in between these two things, I can say, if I get from here to there, I get there by going through some point x prime in between. And that point, I have to average over all those possibilities, right? So what I want is I want to write an evolution equation for this. So for that, what I have to do is I have to now write the probability of being at x at time t plus delta t, and then subtract those two, given x naught t naught. And that's going to be integral again over x prime. And now I will use, so let's just write this patiently. Have I done something wrong? Oh, yeah, sorry. No, for any t prime between t naught and t, this is, yeah. Yeah, so I'll do what, so. What have I done wrong? Have I done something wrong? I think I'm okay. Yeah, okay. And now, let me I'm eventually going to subtract these two and divide by delta t to give you an equation for partial derivative of p with respect to t. Okay? So let me just do that. So this I'll write as equal to integral over x prime 1 plus delta x del over del x prime plus 1/2 delta x squared done this right. Yeah, so what have I done? I have used this result, expanded, and written it. I think I'm doing it correctly. I have this terrible problem that when I'm very close to what I'm writing. Yes. Huh? Yeah, it's really, yeah. On the other hand, I have a different problem. When I'm writing on a piece of paper, I can't write properly. Okay? All right. And so this then becomes I'm missing something, surely. These have to be averaged. Because what I'm talking about is P. Okay? No, because the only thing that's a random variable is the only thing that's random here is the increment, right? Because I'm asking for the probability. X is a representative value. So I think I've done it right. It's just my notation is a little. Okay. So I'm taking this object and expanding it. So when I expand it, the first thing is, so what is random here? Only the step. So what is the thing I average on which the integration applies? Only the step. And therefore I'm all right here. At the moment, we'll content ourselves with keeping only up to second order. Yeah, right. Yes. At the moment, It's true for any t prime in principle, right? Yes, eventually I'll do this only for t. So it should be for t, right? having so much trouble about this. So I can do it for t prime equal to t, so eventually I will. So let me proceed a couple of steps and then go back and do error correction if necessary. I think I'm more or less all right. So now I'll subtract this guy from this guy. Okay. Will be plus dot. What we know, so which you will get with, you will indulge me, just do the integral, right? And you'll get d over dx of delta x times p, etc. Okay? All right? I'm doing a okay, so and remember for the model that we looked at last time, delta x contained only the systematic force, which in general depended on x. And I saved myself really serious technical difficulties by making the noise not depend on x. Therefore, delta x squared will just be a number. And so I don't need to keep it inside. Otherwise, I have to go into another line of technicality about multiplicative noises, which I will not. Okay? All right. And we also saw last time that, for the Gaussian white noise, I've changed my, okay, I've been consistent in delta t. Right? Remember last time we saw average delta x squared was of order delta t, but because the noise is Gaussian, any higher order moments will be passed by that. Right? And therefore, when eventually I'm going to take delta t going to 0, I will not need to keep it. Right? And as a result, I'll get p dot del p by del t is equal to, and you remember we had the mean and we have our equation of motions, we have, where is it gone? Oh, it's here. Yeah, it is here. So the mean will be average of u prime over gamma, and the variance will be our friend kbt over gamma, as you can see. The 1 over gamma outside, if I like. And d will be but we know what that will be. That will be kt over. We can, of course, generalize this to any number of dimensions, and I can do that by writing this as I think I'm all right. This is minus the divergence of p times the velocity. The velocity is minus 1 over, the velocity is 1 over gamma times the force. The force is minus u prime. So I think my signs are actually correct. If I had written in terms of forces, I get a negative sign, but I've written in terms of u. Okay? And this again will be the Laplacian. So if you like, I'll write it like this. Right? So you see several things from this, which again you may have seen before. You notice that clearly you have conservation. That is integral p over all x. And you can see that by seeing that the equation takes the form of the rate of change of the probability density being the divergence of a current. And without erasing too much, I can write. So is this the part that you can't read, or you can read here? Where the current, you can see, has two pieces. One is minus t grad p, and the other is just probability density times the mean drift velocity, which is u, right? That's what I called it here. And now I've got it right, minus, yes, it's right. Yes. Right? Yeah. Happy to pause. Yeah. Again, as I said, this is really elementary foundational material, and so maybe many of you have seen it, but it's useful to state this before going further. Sorry? So I'll say a few things about equilibrium and so forth. So there's lots of things you can infer from this. For example, if you had just chosen an, or let's do it another way. So let's ask, what would equilibrium be? Imagine you had a particle moving in some bounded domain in some number of dimensions. Then clearly, if you got stuff in a box, you know that at long times, at thermal equilibrium, the current should be 0. And the current being 0 means this is 0. And what that means is and what that means is that grad of log p, let's do this right, plus 1 over gamma du. So that means this is a constant, right? Which means that p should be proportional to e to the minus u over gamma d. And with blinding foresight, we had chosen d to be kt over gamma. So is indeed the temperature. So there are actually two lessons to be learned from this. One is that if somebody gives you an arbitrary stochastic process, which in some physical situation has, where zero current is a natural state to study, then for that class of problems, you can figure out the temperature by looking at the damping and looking at the diffusion, right? You can imagine you don't actually have to stick a thermometer in there. You can imagine, and you don't have to construct an entropy and differentiate with respect to energy or anything. You can measure these two quantities and get a temperature. Another point to note is, again, supposing somebody had given you a slightly more general stochastic process of the form x dot equals, in some high number, some more than one dimension, let's say, some function v of x plus a noise. And let me write that noise in this, let's say, as a force like that. And f is 0 mean, is, let us say, twice d times the unit tensor times delta of t. We can generalize a little bit further, but right now let's keep this isotropic. Then what you will find is clearly whatever that v is, it is that v which will go in here, right? So in general, by the same algebra, you will see that and j equals 0 will then mean that d grad p equals BP, right? So naively you might think, oh, piece of cake, you give me a stochastic process, I can always find a zero current solution. But you can't, not in general, because the vector field V has to be curl-free. So if somebody gives you an arbitrary vector field V, you can think of that as a particle moving with a velocity which is equal to, so this is my equation, I just walked past it. Yeah. So unless V is in other words, if V has a non-zero curl, then you can't do this, right? So if you think of V as a drift velocity coming from a mobility times a force, unless that force is conservative, you can't do this, right? But it does tell you that if somebody gives you a problem not necessarily dreamed up out of an equilibrium situation, if you're lucky enough that in that situation it turns out that the drift velocity happens to be curl-free, then it is in effect an equilibrium problem. There's one more caveat, however. Let's explore some of those caveats before we go further. You can imagine a slightly more general problem. Let me see if I can do this correctly. This is the part that I may not be able to do correctly. Supposing F, I can do it right from here. Supposing D is some matrix, okay? Not necessarily isotropic. So for example, D could be, you could be in 2 dimensions, it could have a D1 and a D2 and a 0, 0, for example. Okay? So then what you'll have is, have I done this right? This will be, so D tensor dot grad B, grad P. Okay, so now what you'll have is, you will want D inverse times V should be a gradient. Excuse me. So, from these kinds of considerations, you can look at a general stochastic process problem and see under what circumstances it might fortuitously fall into an equilibrium form. Okay? Yes? Okay. So you can generalize from this in the following way, that what this, if you imagine thinking of this from one time instant to the next, both these terms are telling you about moving in configuration space in some way, moving from somewhere to somewhere else. So a slightly more general way of looking at stochastic processes is to think of a P. So you have configurations called Q, and you have a probability as a function of Q and T, and you could ask, you could say that any general process, first order process, I guess, can be thought of as you are at some point Q, you're going to go to some point Q prime. So if you're at Q, you came from some other point Q prime, and if you are now at Q, you might go to some other point, right? So you could say that in general. So actually, before I go on to that more general case, do I want to say anything more about this? One thing you could do for your own exercise is I've written this as though you just have a coordinate-like variable evolving in time under an external potential, okay? But actually, this form is completely general. What I've done here is I've just said there is a Gaussian white noise, It's a general vector. It has a general covariance matrix. Some of its entries might be 0, some might be non-zero. So actually, in principle, from this form and from this expression, you can write down you can take this case, for instance, you can say that if you have x dot equals p over m and p dot plus gamma p over m equals minus u prime of x plus noise, you can do this, you can, by complete analogy with this, you can write the equation for of x and p and t. That is, you have all the information here to write down the evolution equation for the probability density in phase space as well, known as the Ramaswamy equation. So when you write it in position space, it's usually called Fokker-Planck, and write it in position and momentum, it's usually called Kramers, right? No, I never remember these names, but it's actually useful to know names. Yeah. Huh? Yes? Sorry? All, yeah. Sorry? Smoluchowski is position. What's Fokker-Planck then? Everything? Fokker-Planck is the general, Smoluchowski is position, Kramers is phase space. Position and momentum space. Yeah. I know for sure that this is Kramers. Okay. All right. But you could also take an even more general view. You have configurations. Here's some configuration Q, here's some configuration Q prime, here's some configuration Q double prime. You can think of your evolution as simply taking you from one point to another, stochastically, okay? And then you can say what you really have is your probability. So if you're at Q now, you got there from other points Q prime by some transition probability from Q prime to Q. Has someone in these lectures already done the mastery equations? Okay. Sorry? Huh? Okay, all right. Right, so this is gain, the point Q, here is Q, here is other points Q prime, and you're going from there to here. Okay, and here is loss. You could go to other points, which I'll again call Q prime. It doesn't matter because I'm going to sum over them. So I can remove this summation from here. And from this point of view, if you think of configuration space as a set of distinct points on which you can just put labels, P of Q is just one of the components of a big vector, which is probability here, probability here, probability here, probability here, probability here, etc. Right? So, this is d over dt of some probability vector is some operator on that probability vector. Now, I won't spend much time on this. On this language, I'll stick to this language. Now I will go back to my notes. I have to find my page for that. These pages. Just give me a minute. But for what I'm now going to discuss, a good place to look it up is There are many ways to think about why this more general formulation merits our attention. One of them is that even notion, we tend to think of thermal equilibrium as something taking place of particles moving in space in a potential. But actually, thermal equilibrium is a more general concept than that. And even if the set of configurations Q, Q1, Q, etc., were kind of scattered in some fairly arbitrary way and not to be thought of as points in space with a local spatial distance, you can still talk about equilibrium. You can still almost talk about the notion of a gradient flow. You can certainly talk about the analog of that curl-free condition that I just rubbed out. Okay. So let's see that. And the reason we want to do that is we want to move towards talking about entropy production. And entropy production, we will find a natural way of thinking, definition of entropy production, which we'll then use in analyzing some active matter models. So let's do a little bit of algebra. You can see that in general, having a steady state here, just as in, do I have it anywhere? Yeah, just as in general for a steady state in a spatial kind of system, steady state only requires divergence of J to be 0, not J to be 0. Likewise, a steady state in general only requires this whole object to be 0, and not every entry in the summation individually to be 0. But here again, there was a special class of steady states which was J equals 0. And there will be a special class of steady states in which this whole summand itself, summand, this is what it's called, the thing under the sum, is 0. We'll come to that, and we'll understand it in a certain way. What we're going to do is, let's define the entropy the way we heard it defined in other lectures such as Dov-Levine's. And I'll try to keep track of factors of Boltzmann's constant, but it doesn't really matter. Sorry, my notation is bad. I'm calling these, let me call these P, let me be consistent with my notes. By which I mean and this could be in any number of dimensions. I'm sorry? No, think about it. This is P. Entropy is KB times the log. Okay, let's take a special case. Supposing you were uniformly distributed. Supposing you have a space, and let us say that space has some volume omega, and P is uniform. For example, then P equals 1 over omega, right? That minus sign comes because you're talking about the log of how much space you have access to. P is really the inverse of that, right? The more concentrated you are, the less you have access to. I just wanted to write it as k log omega. Anyway, yeah. And now, this is a definition which I will not try to justify because it's been used now by earlier lecturers adequately. Right? So what we want to do is we want to look at the time evolution of this quantity. Given, sorry? Longer chunks. S is only a function of time. S is, you've integrated over all of the configuration space, so S is only a function. Of course, again, I told you I'm doing this more generally, and my notation's already gone bad, right? I've gone from sum to integral. Let me stick to my original notation. Yeah. Because I don't even want to assume that I've got some, smooth structure on my space of Qs. Let me do it without that. Because I'll never differentiate with respect to Q anywhere in the immediate future. Okay. So ds over dt is minus kb, sum over Q, p dot of Q, p dot log p, plus p dot. Agreed? Yes, because the second term is p times the derivative of log p, which is p dot over p. Right? The sum, this term, so if I put in the argument, the second term is the time derivative of the sum over Q, p of Q. So I only have p dot log. But p dot from our, this is called the master equation. Is I think my notation is not the same as Schponel. It's just, labels have been changed. So as Dov would say, names have been changed to confuse the innocent. So let's rewrite this slightly differently. Let me just leave these guys out for the time being. Since I'm doing a sum over Q and Q prime, I can symmetrize this over Q and Q prime. Okay? If I symmetrize, then I can write this as, let me absorb the minus sign and moving these guys around. I'll write it as KB over 2, sum over Q and Q prime. Which I can repack in this form. Hope to God I get it right. I'll just, sorry. Have I messed up somewhere? I just took this, I rewrote it by interchanging Q and Q prime everywhere. That's wrong, of course. No. I think this is right. No, maybe it's the other way around. Hang on a second. No. This is Q prime. Now I think I'm okay. Unless it's become this. Oh, now it's become the same as this. No, sorry. Excuse me, hang on. No, this is Q prime. Damn it. Just a second. This is Q prime Q. This is P of Q prime. This is Q prime. This is P of Q. Now I'm okay. Okay, folks. Yeah. Q prime P of Q has become Q prime P of Q prime. Q prime Q P of Q prime has become Q prime P of Q. I'm in good shape. And this was Ln P of Q has become Ln P of Q. So now I'm okay. But I can just repackage these as, and now let me do it, right? Q prime P of Q. You know, the students are supposed to catch me on this, not the grown-ups in the audience. Yeah, that's the other property of students that worries me sometimes. Times, now let me make more room and write this. This is important, so let me write this properly. Let me write here. Q and Q prime. There's a log of now I have to do a fairly large amount of rearrangement, which I will not drag you through. I will say this can further be rewritten by further rearrangement as the following, as two terms. This is just, I haven't said what these terms are, okay? And let me now some space. I'm suppressing the T index. T is there everywhere. All of these are in principle expressions valid at each point in time. I'm just saving myself the trouble. So all of these guys have got a T there in principle. Yeah. Even more room. Log. So that I claim this is one piece, and now I have to also give you an expression for the other piece. This is JS before I do the averaging, and when and average JS is, I shouldn't even write, I'll just call it average JS. Okay? It is this average in general depends on time. So this is, I mean, you can convince yourself in the privacy of your own room by just taking this expression, taking these expressions, doing the sums, and seeing that you get this expression. You may ask, why on earth am I doing this? Okay, so you will see in a moment why I'm doing this. Yes. Oh, sorry. Let me write it here. Again, it's the students who should tell me. Or maybe only Srikanth can't read. So let me, again, attempt to do this. You can't read the JS thing or both. This is okay, right? Yeah. I should have said that the W's, right from the beginning, I've taken to be time independent. Okay? I mean, just looking at what I unfortunately rubbed out, you understand that the W's are simply transition probabilities per unit time to go from a given point. If you're at this point, your transition probability to go to some other point is that guy into delta t. Okay? So what have I done? I've done some weird-looking manipulation. Take this rate of change of S, whatever it is, to a certain form involving two pieces, and I've somehow called one of them. This is going to be entropy production, and this is going to be the average of the entropy flux. I mean, but it's not so obvious why at the moment. Okay? What you should understand is the following. Supposing you're in steady state, then there are two possibilities. One is that steady state is that very special kind of steady state where no entropy is produced at all. Or the other is where, locally all kinds of dissipative processes are going on producing entropy, and you're in a steady state, so you can't hold any inventory of entropy. You have to ship it out as you get it. And the steady state consists of a balance between production and shipping out. It makes sense for the so the claim is that you should regard this term as the shipping out and this term as production. To see why, at least let's see one thing. I guess I can erase this. You know that for any two quantities, this is A, this is B. This is A minus B times log. Not log A minus B, what have I written? Terrible. You're welcome to prove that for yourself. Okay, so what that means is space. Let me write it here. This means that sigma of t is greater than or equal to 0. And only if our friend So we've been able to separate the entropy production rate, the global entropy production rate, into two pieces. Note that even for a stationary state, ds by dt, that quantity we started with, is 0. Okay? So what must be happening in a steady state in general? So let's now discuss steady states. The reason ds by dt equals 0 is that s depends on the probability distribution p of q and t. And if p of q and t is independent of q and t, or independent of t, then ds over dt is 0, right? And in that case, we have a general steady state in which this thing which we're calling production balances this thing which we're calling flux. But in the special case, in this case, both are separately 0. And again, you've seen this before, but let's understand this. Oh, God, terrible. So as I say, no. This is the unaveraged guy. Yeah, this is the Q dependent guy. And yeah. This is the. Oh God, where? Yeah. So I'm leaving out t's at various stages. I've not been very. You're right. Then I'd have to make more board space. Sorry. Yeah, but I'm just saying that locally, in principle, can you imagine a situation in which sigma t is 0, but p is time dependent? Yeah, clearly. Yeah, right. If the W's are time independent, then unless P of Q T over P of Q prime T magically is time independent, you could imagine, yeah, so I don't know. Sure. Conservation might actually do it out. Okay, don't know. Okay. All right. So, I can erase this. So this grand ambition to tell you about those experiments, etc. Let's see how far we get. I will not force myself to go fast. Okay. So we've discovered the special class of steady states, which we could have guessed at from the beginning, but which have been given an added significance. So sigma equals 0 gives you the condition that is known as detail balance. You know that condition of detail balance just by looking at our starting point, which I've rubbed out. Remember, our starting point was dp over dt was sum over q, wq q prime dq minus wq prime q pq prime. And I told you that you could have a kind of highly restricted kind of steady state where this thing is 0. The summand itself is 0. That's called detail balance. We've rediscovered detail balance by constructing an object which we call the local entropy production and finding that it vanishes. Okay? And pictorially, you know what this means. Here is a point Q, here is a point Q prime. The idea that PQ, WQ, Q prime is equal to PQ prime, WQ prime, Q means that zero net traffic between any two points in configuration space. So I have done a little sheet here Okay, this is reasonably gentle, doesn't matter. So what's happened here basically is we've said is this point absolutely clear to everybody that this object being zero, that these two things being equal means that you look at this abstract network of abstract set of points which is configuration space, you pick any two, it doesn't matter where they lie. Obviously, if the W's going between them themselves are zero, then you have no track between those two. Right? I mean, I'm saying that imagine random set of points and some sort of matrix of W's which connects some of them. Then if there is a pair that's connected by a little pipe allowing stuff to go, this condition says that the net flow through that pipe is zero. So, occasionally something goes this way, occasionally something goes that way, and it precisely balances out because that's what this expression says. Okay? And it's clear that a stationary state of that sort is time reversal invariant because so what does it really mean? It really means that if you imagine running a great big experiment or simulation. Imagine running a great big experiment, capturing all the data, and then giving it to your colleague after delabeling time so it's backward. Your colleague will not be able to tell, barring transients. Once you're in steady state, your colleague will not be able to tell whether the movie is being played forward or backward. Okay. So it's and this, okay, now, so this is fine. The trouble, however, is that the condition of detail balance, as described here, is a property of the W's and the P's. The dynamics is defined only by the W's. So you'd like a condition of detail balance that doesn't say anything about the P's, just something about the W's. Somebody, reaches into their bag and hands you a set of W's. Is this equilibrium or not? So, time reversal invariant, detail balance, thermal equilibrium in a certain sense are all equivalent. Okay? We'll see in slightly more detail why, probably at the risk of, it doesn't matter. Maybe I can show them the other stuff in. Sorry? Right, yeah. So another way of writing this, so to try to figure out, so what we want is, can I write down a criterion only involving the W's? That gives me detail balance. And by the way, the reason you need that is when people tell you about, suppose you're doing computer simulation, they'll give you a set of rules, and they'll those rules, if you're doing a thermal equilibrium computer simulation, have to respect detail balance. So you'd like to, of course, often. No, that's fine. Yeah, I think that's my statement is correct. So let's try to explore this. By the way, you should note that this situation, if the Q's are actually spatial coordinates, can be rewritten as a zero current statement, and ultimately can be written as a curl-free condition. So let's try to understand this. Another way of writing this is to say that let me call P0 the steady state distribution, okay? P0 of Q prime over P0 of Q. So you can see already that you're putting in this way of writing it, you're saying somehow that the ratio of the two transition probabilities, the transition probabilities per unit time, is the ratio of some quantity that depends only on the final point to, there exists some function such that this ratio is the ratio of that function evaluated at Q prime to that function evaluated at Q. Or to put it another way, the log upside down. And now it's starting to look like a condition of something being a gradient. Some quantity, which in principle depends in some arbitrary way on Q prime and Q, is the difference of some property evaluated at Q prime and that property evaluated at Q. So it's beginning to look, if this Q prime and Q were nearby points, it's like saying that this guy is roughly the gradient of some function on Q space. Right? So it's beginning to look like, but it's more general in the sense that you don't have to have a notion of distance on this space to talk about this. Am I making sense? Am I repeating myself? Yes? All I'm saying is that this condition, rewritten through these two elementary manipulations, is saying that the ratio of the transition probability this way and the transition probability that way is the difference. There exists a function on configuration space such that the transition probability along and against a given bond is the ratio of the log of that ratio is the difference of a property evaluated at Q prime and that property evaluated at Q. Right? Yeah. Meaning you don't need to know P0. And after all, until you solve the equation, you don't know P0. But this tells you that this thing has a gradient-like character. If you think of Q and Q prime as nearby points, there's a gradient-like character. Okay. So let's think of a sequence of configurations. Here is configuration 0, configuration 1, configuration 2, blah, 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 configuration n. And let's write down W01, W12, W23, dot, 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 Wn minus 2, n minus 1. So let's say this is 0 to n minus 1. There are n configurations. W n minus 1 to 0. And let's divide it by the reverse. 1, 1, 0. What is that going to be? This 0 to 1 divided by 1 to 0 is P0 of 1 divided by P0 of 0, right? This guy and this guy. 1 to 2 and 2 to 1 is P0 of 2 over P0 of 1. Dot, 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 dot. And P0 of n minus 1, P0 of n minus 2. So now you can see, so I took this, I looked across here and rewrote that ratio as P01 over P00, looked across here, rewrote that as 2, 1, etc. Now I look across again and notice that this cancels this. I notice that this cancels this. The guy here will cancel this, etc. This will be equal to 1. Okay? So we have discovered our condition on the W's. So notice I worked with the P0s. I didn't know what they were, and I found they fell out of the equation completely. Right? So for any loop in configuration space, going from 0 to 1 to blah, blah, to n minus 1 to 0, this product has to be 1. So we have found a condition. So the condition is that this, for an arbitrary set of configurations, this condition has to be unity. This object has to be unity. It's got a name. It's called the Kolmogorov curl condition or something, or criterion. It's a condition. It's a condition for the steady state. Actually, it's a condition for the steady state of a stochastic process defined by a set of W's to be a time reversal invariant steady state, to be a detail balanced steady state. Okay? And the reason we like it is because you don't need to solve the problem to know it. You can do a diagnostic on the W's. You don't have to run the problem numerically and discover the P0s. You don't have to solve the problem analytically. You know a priori whether it will or won't. Okay. Yeah? And this is really analogous to the condition we wrote down much earlier in the context of a stochastic process on a set of spatial coordinates, where we said that if you want a zero current condition, then the drift term has to be curl-free. It's the analog of that for an abstract set of W's which aren't necessarily metrically related in this. So by the way, given this picture, you can actually discover what the energy function is up to a constant, which is of course fine, in the following way. You pick any, here's some configuration Q0, and here is some other configuration Q. Okay? You just take log W Q0 over W Q0Q and write it as phi of Q minus phi of Q0. Right? Remember, we said that this ratio has to have this property. We don't know P0, but what we can do is we know the W's. Right? So what I'll say is, I'm going to set phi of Q0 to 0. I'll just say I pick some Q0 as my starting guy, my reference. And just like you do with the conservative force fields, you do an integral from some reference point to the point in question and discover what the potential is. You can do that without even doing an integral. You can do that just this way. You take this guy, you take this guy. For any Q1 and Q, any pair of Q and Q prime, you're given WQQ prime. So do that for some arbitrary reference one and this guy, and say I'll call this phi of Q. Okay? Then you go to the next point, Q prime. Then you say that you take log W Q prime Q over W Q Q prime, and you say that has got to be phi of Q prime minus phi of Q. Okay? But you know phi of Q, and you know this, therefore you know phi of Q prime. Right? So phi of Q prime is phi of Q plus log. I've done it right. So now, by doing this, by taking a walk over the entire configuration space, you can label each point uniquely up to an overall additive constant by something called phi. And you know for sure that P steady state of Q will be divided by a normalization. And the normalization, of course, is just the sum over these. So you discover thermal equilibrium. The point is, merely writing P this way doesn't tell you anything. You can take any P and write it as the exponential of its own log. The point is not that. The point is this. Okay? Yeah. There's nothing consecutive. I arbitrarily labeled them 0, 1, 2, etc. so that I didn't have to put, I just called them 0, 1. I just labeled the points. Anyway, in any order. Yeah. Just, the order is just for the purposes of writing this down. Yeah, so now in the remaining 10 minutes, let me tell you the following. Now what we want to do, so that is, by the way, all of you who do computer simulations, you know the Metropolis method. Check that the Metropolis method obeys this. Obeys this. Equal to 1. How many of you don't know what the Metropolis method is? How many of you were at Dan Frankel's talk in faculty hall at IISc? Or here? Did he make the same joke or same information? Okay. How many of you know the Metropolis, the fact that the Metropolis method is named after Metropolis, or it's being recorded, right? Is he alive? Is an example of the famous theorem that all famous results are named after someone who didn't invent them. Yeah, so anyway. So read about the Metropolis method. So let me spend a little while going back to so what hopefully we've agreed is that this object, so we sort of by repetition and intimidation, I hope I've convinced you that P of Q times W of Q to Q prime minus P of Q prime times W Q prime Q or is a measure. It measures time irreversibility. It measures the difference between forward and backward. So if you have a stochastic process for which this is zero, identically for all pairs Q prime, that's a time reversal invariant steady state. For a more general case, therefore, and now I'm just going to argue by, just words. If you've got a process going from some point to some point, Q1 to some point Q2, then the probability of going from Q1 to Q2 in a time t divided by the probability of going from Q2 to Q1 is a measure so now I'm really not going to derive the precise way in which the quantity that I'm going to now use is really simply related to what we're doing, because I just want to give you a flavor of the kind of thing we're doing. So what I'm going to do is I'm going to take, I've forgotten where in my notes I put it. I had a lot more. Oh, one caveat I wanted to tell you. All of this is fine if the dynamical variables involved are themselves even under time reversal. Why? Let's give you a quick example. Can people see here? Srikanth, I can write here? Yeah. So just to tell you, you should, those of you who are really paying close attention should panic when they see this. Why? Let's take a harmonic oscillator at thermal equilibrium with positions and momenta. Okay, so supposing this is the momentum and the position of a harmonic oscillator. For a given initial condition, if I am at a positive coordinate value and a positive momentum, I'll go outwards, right? I'll go like this. And you can put in thermal noise now into this. It's not as though you'll typically go around this way as often as you go around that way, even though you're at thermal equilibrium. Time reversal invariance for a problem with a position and a momentum means the probability of going from this point to this point is related to the probability of going from these 2 points. Why? You have to, so going from QP to Q prime P prime and going from Q prime minus P prime to Q minus P. So if the degrees of freedom in your problem are some of them position-like, some of them momentum-like, you better implement time reversal on all of them. Okay. Right through this discussion here, I've been pretending that the variables involved are invariant under time reversal. They're all position-like variables. I've been working with the inertia-less Lingerie equation, working with the Smoluchowski or whatever it is. Okay. That's one caveat to keep in mind. So let's, in the last 4.5 minutes, tell you a little bit about the active particle problems. It's not really essential to tell you much. Oh, I didn't say anything about the Js. The point is, in equilibrium, in equilibrium, both terms will separately be 0. The average Js will be 0, and sigma will be 0. In general, there's only a no inventory accumulation, no pile-up condition. But here, actually, there's no delivery, and therefore there's no production. Therefore, you don't have to deliver stuff. Right. So average Js also 0. Indeed. In any steady state where one of them is non-zero, the other will also be non-zero. And so I was going to talk about an example of such a steady state. Yeah. So let's... no, this is the one I didn't want to erase. Well, it doesn't matter. So... active... let me just write down the equation of motion and then tell you what it is. Supposing I've got a particle, as I said, I'm sure my notation has changed again, but got a particle with, I've got a timer, okay? The center of mass is capital X, the relative coordinate is little x. I know I've changed my notation. And you remember we agreed that the equation of motion for this, if I throw away inertia, zeta delta mu is that way of introducing non-equilibriumness. And so imagine that I've gone through the process of coupling my dimer to chemistry. I've held the driving force on that chemistry constant at some value delta mu. You remember that whole formalism that I spent a long time on, right? Okay. And I argued that in general, if you do that to this problem, you'll get, in principle, you're allowed to get a term in which instantaneously the dimer is extended in some way. It starts propelling itself in that way. It's this term. So let's just show ourselves that, but this is just algebra, so I will not do most of the algebra. I'll just tell you what we do, okay? We calculate probability, capital F and little f are noises. And in response to a question that I think you asked, at the moment we're still pretending the noises still come from the same thermal bath. We have a fixed thermal bath, we only drive a chemical process in one direction. So then it's an elementary exercise. So okay, first of all, then, what is the quantity we're interested in? If we want to calculate probabilities of forward and reverse processes, we want probabilities of paths, right? X goes from some point, the probability that X executes one particular motion from, say, some initial point to get my notation fixed. It starts from some xi at some t initial and ends up at some xf at some t final, right? What is that going to be? I claim we actually know that because I told you how these forces are distributed. Right? Recall I told you in the last lecture that, for example, the probability distribution of that force capital F is e to the minus 1 over 4 t gamma times integral dt f squared of t. Okay. So let me just assert, therefore, that the joint probability distribution of big X and little x will be some object which I'm calling A, where A is the integral from the initial time to the final time of just what you get by saying that if these are the equations of motion, then basically the probability of the stuff, take all the stuff except the noise to the left-hand side. The probability of that guy and the probability of that guy are proportional. There is a technical issue about the type of calculus you use, which does not affect our answer, right? In particular, it does not affect our difference between forward and back. So what we'll do is we'll write down the action. It will look like this. So right, where this comes from basically, oh, I'm sorry, I didn't tell you what these guys were. Let's take the particular case of little x just being a linear spring, a Hookean spring, okay? So you've got this dimer, and you can say that this guy is just a little Hookean spring with spring constant. Okay, sorry. This is A forward, and you can, so yeah, the A reverse will be these guys, but with t going to minus t, okay? Or more precisely, t going to t final minus t and redefined times, okay? So I don't want to do the algebra. I'm just saying that I told you what the path probability, what the probability distribution of the noise was. Therefore, you know the path probability for the dynamical variables. Therefore, you can calculate probabilities of forward and reverse processes. Okay? And what you will find is, the only result I really wanted to tell you about is that you can construct these objects. You will find that A reverse minus A. I mean, supposing you did this for a particle under the action of an external force, you will find basically the power dissipated, okay, divided by temperature. Similarly, what you will find here is, for this particular case, you will find something like, let's take an ultra simple case, and let's assume that both these guys are bound by harmonic springs. So over big X is also some other spring constant times big X. Okay. Enough. Okay. You can also do the time reversal a different way, and I'm telling you why would you want to do this differently? The point is, you have a system. This is a system which you know is not equilibrium because you prepared it by running some chemistry in some directed way and seeing what happens. All you want to know is how much like equilibrium is it, or how much like equilibrium is it not. Okay. In particular, you will find that if you leave this noise out just for fun, you can turn this into an equilibrium problem. I'll just tell you that in a second. In which case, in one description, this problem imitates an equilibrium problem. You should be able to compute an entropy production which is 0. So I'll just come to that in a second. How much time should I, 2 minutes? 3 minutes? Okay. This is if you do t to minus t and you don't reverse but if you do t to minus t, x to x, and little x to minus little x, you get a different result. You get And why is this interesting? This is interesting, I'll tell you. Experimentally, the point is, in principle, if you're an experimenter playing with an active dimer, you can sample all the dynamics, you can assemble, you can accumulate trajectory statistics for all kinds. You can accumulate trajectory statistics for this type or for this type. In this type, what's happening is your dimer is like this. You're looking at the probability of the dimer going forward along some path and coming backwards, but not turning its head around. if little x, if you thought of little x as kind of like a velocity of this guy, kind of like a momentum, and if this was an equilibrium system with big X being a position and this guy being a momentum, then that's not the question you'd ask. As I said, when I talked about time reversal, I'd reverse the velocity also. So in principle, you're entitled to ask in your huge grab bag of trajectories, the relative probability of a forward and a reverse trajectory where you reverse the dimer polarity. And you get different answers. The last thing I want to say is, you can construct an object. Okay, and the last thing I want to say is that if you take this very problem, the last but one thing I want to say. You take this problem, throw away the noise, the thermal noise on the x coordinate. Then you can take these two equations for the case where h is quadratic in big X and little x, and rewrite them in the form, I hope I have that form somewhere where I can find it. Yes? So if I set noise on center of mass coordinate equal to 0, then I can write the whole problem as elementary algebra. You can go through it yourself. It looks like an awful dog's breakfast, but actually it's just times the noise on the relative coordinate. Okay? So what I've done is see, this equation is x dot, it's got a little x in it. You can differentiate it one more time, and you will get stuff involving little x dot. Little x dot you can get from here. You do a little bit of algebra, but the end result is the fact that, see, if you look at this equation, if you think of this as being, if you think of little x as a velocity, this is like a damping. So in many ways, except for this, the trouble posed by these pieces, this coupled dynamics looks kind of like the coupled dynamics of a position and momentum. A persistent polarity variable for this dimer is kind of like inertia for a velocity. Okay? And that manifests itself in great detail here in the following limit. Supposing, this is general, supposing h was purely quadratic in capital X, then this term is just capital K. Right? And now you have something very interesting, which is that you have something times x double dot, a constant times x dot, an external force, which in this case of per force has to be kx minus kx, and a noise proportional to the activity. This noise is inherited from the noise in the little x equation, promoted to a noise in this equation. Right? This is algebra that you can do in your spare time, if you have really nothing better to do. Just take this. So the reason this illustrates several principles. One, it says that the existence of a positional noise, a translational noise in this first equation is really important. If you throw it away, you can reduce the problem to an apparently equilibrium problem if the potential in which the particle is moving is quadratic. Because then this coefficient turns out to be a constant. So now, the reason I've written it in this somewhat complicated way is to keep the force as a force. I don't want any stray coefficients in front of it. Okay? So this is an effective mass which has nothing to do with the original particle's mass. It comes from the damping coefficient on the internal coordinate. An effective damping which is the original damping plus a funny combination of the internal damping. The original force acting on the center of mass. And a noise which exists, which is conveyed from the internal coordinate to the center of mass only because there is activity. So this is a classic example of an effective temperature problem. So here is a case in which you can turn activity into temperature. The crucial point to note is not just that activity is some random agitation. Activity takes the random agitation on the internal coordinate and transmits it to the center of mass coordinate explicitly. There are many problems in the active matter game that look like this. For instance, suppose you have a membrane and you have little force generators, pumps diffusing around. Then if so you've got some membrane and some pumps sitting around in it. Imagine these guys are diffusing. Imagine you forget about the intrinsic thermal fluctuations. If these pumps locally pull on the membrane, then their entry and exit into a given region will produce a fluctuation whose size depends on the diffusivity of the pumps, but which is proportional to their activity itself. So there are many instances of this. So this is one of the simplest. So this problem, in this limit, if I switch off F, and these forces are linear forces, quadratic potentials, then you get an apparently thermal equilibrium problem. The steady state here has to be time reversal invariant. So for this problem, if I switch off the intrinsic noise, the positional noise on the joint coordinate, it actually becomes an effective thermal equilibrium. If you calculate entropy production for this, you will get 0. Okay? Now the question is, what happens when you how do you interpolate? So how do you interpolate between that and these results? It's not as though I can turn these to 0 by switching off the noise strength. I don't see the noise strength anywhere here. I don't see this noise strength anywhere here, right? So it's not as though the presence of this noise strength anything is responsible. How do you interpolate smoothly between this steady state and that one? They are two very different steady states. When you switch off this noise, you rule out completely the possibility of this particle going backwards without turning around. Right? You've got a dimer. It goes like this. It can only go backward. It can only go the other way if its nose is pointed the other way. So you've 100% ruled out one class of processes. The way to do it, it turns out, is to calculate a frequency-resolved version of the entropy production. Something called sigma omega, which I can't write for you right now. And you find that, let us say you take this case where you don't reverse the x and construct the entropy production. It ends up looking like this. Ends up looking like the python that swallowed, the boa constrictor that swallowed an elephant in the Little Prince. Okay? And as a function of frequency. It's substantial only at frequencies in between two crucial frequencies, which are I'll close with this. I'll really end with this. Really and truly. Promise. Yes. But I will. I'll just give you the frequencies and I'll stop. One of them is little k over gamma, and one of them is the time it takes the particle to equilibrate in the joint potential, which I guess is big Q. Just say it correctly. Just give me a second. I'll close with this. So let me draw it slightly differently. It will go as omega squared and omega to the -2. Between the frequencies, there'll be two frequencies, which is, one is k over E gamma, which is the relaxation rate of the internal coordinate. And the other is the time, the other is basically, it's big K over big gamma, So the point is the following. If your relaxation rate of the internal coordinate is too rapid, then this term here doesn't look like a colored noise, basically a white noise. So supposing this is really fast, rapidly relaxing, then the time scale that you're talking about on which you'll see its correlations is short enough, you can just lump it into the white noise. This just becomes an ordinary equilibrium problem with modified temperature in that level. The other is, how long does it take for this coordinate to feel this noise? It takes a time having to do with the equilibration of the center mass coordinate in its potential. Okay? And unless you wait that long, imagine that time is longer, unless you wait that long, you don't know this noise is there. Have I done it correct? Oh, this on time scales. Damn it! These are frequencies, right? No, the way I plotted it actually is the inverse frequencies. Sorry. And if I look at time scales smaller than too small for the translational noise to have acted on this coordinate, I won't know this term is there, and I should get no entropy production. If I look at on timescales such that the colored noise has sort of done its stuff, then again it'll be an equilibrium problem. So this is the last thing I wanted to say. This is for this case. The other key point I mentioned is the fact that you get a different result for the entropy production if you reverse the polarization. So these are sort of relatively technical points which I thought it was okay to bring in at the end. That's the end of my lectures. If people want to know about these other things, maybe we can talk about them in, it doesn't really count as a tutorial, but